anything.
Okay, so bring them on. Let's go through some questions. So Maisie asked a very good question. So kind of putting this in context, the chain rule. The chain rule is just what turbocharges our regular derivatives, right? Anytime you ever have a derivative that's got of a composition of functions, meaning a function that's got layers to it, right? Functions of functions. Anytime that shows up, whether it's inside the quotient rule or the power rule or whatever, you have to, that's when the chain rule comes into play. So here's what we did last Thursday, right? We just looked at a bunch of problems like this. You guys pulled up some problems you wanted to go through from the homeworks. And I think, didn't we kind of get up through, did we do through problem set 3? Is that what we were kind of working on? Okay. Okay, and so it was problem set 4 from what sections? 2.4, this one. We can change all these dates, and obviously these dates are probably need to change. We can do that. Don't worry about the dates. That's the one I think we left off on, right? Okay, so why don't you look through that and see if there's anything in there we need to talk about. And then when we're done with that, if and when that happens, well, it's going to happen, but when that happens, then we can kind of proceed with our review of logs and exponential stuff, pre-calc review.
Okay. Can we do, did I get that one right? I think I have it.
Okay, so this is our u and that's our v, right? So we're going to get u dv. Well, here's the chain rule, right, Maisie? Here's what we're talking about. If we're going to differentiate, this is a product rule issue, but the derivative of v, well, that's a layer, right? I've got some function cubed. And so that's where I need to use I need 2 links in my chain for the 2 layers in that function. So I'm going to get 3 times hand squared times the derivative of hand, which is 3. And if we were to, what could we do here? So we were going to, we made this a 9 times 3x minus 9 quantity squared, and here we have a 3x minus 9 quantity cubed. And so what did we do? We pulled out a 3x plus 9 quantity squared, and then we combined all this into 12x minus 9, and then we just, right?
I'm looking.
Because this is, what is this? This is just u v prime plus v u prime is just 1. Okay, but here's, the chain rule comes in only in one spot. The chain rule comes in right here.
Yeah.
Okay, that's it for the chain rule.
No, I think I understand. I was just in my message for it.
Yeah. All right, but then we could have factored out, see, that's not right. We could have factored out a 3 squared, which would have been a 9. We factored a 3 out of there, so that should have been a 27.
3 squared, what do you mean?
Well, because look, if I were to, I could write this one as, I could write that as the quantity 3 times x minus 3, all squared, right? Inside the parentheses, I could factor a 3 out of both terms. Everybody see that? So this is kind of good to see, probably. And I have a property of exponents that just says, if I have a times b to the m, that's just a to the m times b to the m, right? So if I've got the product of 3 times hand squared, then that's just 3 squared times hand squared, right? Well, 3 squared is 9. And then here I could factor out, I could break that up into 3 times 4x minus 3. And so now I've got 3 times 9 is 27.
Oh.
Right, so all this stuff right here would just combine into 27 now too.
Okay.
Okay?
Great.
Make sense?
I think I kept getting wrong was like, I would factor out the 3, but I wouldn't, square it again.
Right, okay, so you gotta be careful with that. You can't factor that 3 out because the 3 is being squared. What you'd have to do is factor inside the parentheses and then break that up into a 3 squared times an x minus 3 squared.
Wait, so on here it says it's 2 times.
Mm-hmm. Should be 27.
But it should be 9.
Should be 27.
But where do we get the 12 minus 9, 12x minus 9 from?
That's because that's what was left over when we did the derivative, right? And we just simplified this first term a little bit. We just said that 3 times x is 9x. And then we're left with a 3x minus 9 squared. And then over here, we just had a 3x minus 9 cubed. Well, we've got 2 terms, right? I've got this first term plus this second term. Each of those terms contains a common base, a factor, a power of the base 3x minus 9 squared, right? Here I've got a 3x minus 9 squared. Here I've got a 3x minus 9 cubed. We have a power of the base 3x minus 9. Here it's squared and here it's cubed. So we can factor out the least common power, right? So the smallest power of that base is squared, so we can factor out a 3x minus 9 squared, which gets rid of that one. So from the first term, we're just left with 9x. From the second term, we do this. That's the same plus sign, right? From the second term, if we divide 3x minus 9 cubed by 3x minus 9 squared,
Oh, we can
We get
add
3x minus 9.
the 9x to the yes.
there, exactly. Okay? Good? Okay. All right. Anything else from that? Yes, sir.
Could you tell me how to do derivatives of log functions real quick?
Derivatives of log functions.
Yes.
That's coming up.
So don't do that aside.
Don't do that side of it. No, I put those up there, but we're not there yet.
Thank you.
So the through 2.4 practice 6, you really can't do yet, because we haven't talked about that. Yep.
Okay, so this is on 2.4 practice 4.
Mhm.
That's number 4.
Number 4, okay.
Find the tangents of the curve y equals 4 cotangents of pi x over 8x.
Okay.
Oh, Can we go over?
2.4 practice 4? Yeah, okay, so you had requests for 4 and then 5. Let's look at both those. This is 2.4, practice 4, number 4. Okay, so let's talk about this one now. If we want to find the tangent to a curve, remember all that means, it sounds hard, but all that is we just need a point and a slope, right? The point is pre-calculus stuff. If we know what x is, we can evaluate the function at x to find y, right? So what's the point of tangency going to be for this guy? X is 1. And we're going to get 2 times the tangent of pi fourths. What's the tangent of pi fourths? 1, right? So we're just going to get the point of tangency is just 1, 2. And then if you want the slope of the tangent line, that's just the value of the derivative at 1, right? So right? So you're just going to calculate y prime. That's supposed to be at.
Wait, how is that supposed to tangent at pi over 4, what?
Well, what's the job of the derivative? It tells you the slope, right? Slope of the curve, which means the slope of tangents to the curve, right? So the slope of the tangent line is just going to be the slope of the function at x equals 1. So we'd have to calculate the derivative function and then just evaluate the derivative at 1 to find specifically the slope of the curve at that point, which would be the slope of the tangent line, right? Everybody makes that connection, correct? The
But
slope
how
of
did you know that the slope of the tangent line at pi over 4 is 2?
would, I don't know what it is yet. We haven't calculated it. That's just an at symbol. So the slope of the tangent line is just equal to y prime evaluated at x equals 1, right? But we don't know what y prime is yet. There's y. So we'd have to fill in the blank, y prime equals something, right? Function of x, and then just evaluate it when x is 1. Oh, are you talking about right here, how we got that?
Yeah.
Oh, I got you. Okay, well,
I
that's,
just want to know if that was an accident or not.
no, that's 2, because that's just the value of, if I plug 1 in for x, what do I get? I get 2 times the tangent of pi fourths. Tangent of pi fourths is 1.
I know the tangent of pi fourths is 1.
Well, you hit circle.
Because sine of pi fourths is square root of 2.
That's the place where sine and cosine have the same value, right? The coordinates are
Oh.
square root of 2 over 2, square root of 2 over 2,
So I would have had to do a triangle.
right?
That's a lot.
Yeah. Yeah, the triangles are fine, but I really feel like it's worth, the unit circle, it's just worth being really familiar with those points on the unit circle. It's, in college, they'll expect you to do that. Yeah. That make sense? So this would be one where when we take the derivative, I've got the tangent of a function, so I need the chain rule, right? I've got a tangent of hand, but hand is not just x. So I'd have to have 2 links in my chain rule. Okay? Make sense? You guys good on that one? Okay, number 5. Okay. So this kind of takes us, to me, this is a much, much easier problem to do because the derivatives of the exponential function is so easy that it makes this one a lot easier. It probably looks a little bit scary at first because it's got logs and exponentials in there, but that's why we're doing an extensive review of that stuff. We have to de-scarify that stuff. It's really not meant to be scary. So we just need a point of tangency and a slope, right? So what's our point of tangency going to be? The point of tangency, the x value is 1/2 log 2, right? What's y going to be? Well, I'm going to evaluate that. So y is going to be e to the 2 times 1/2 log 2. Right? And I know that probably looks a little bit scary, but that's all we do is we're just going to evaluate the function at that value of x, right? That value of x goes in there for x. And if I simplify that, well, what is 2 times 1/2 log 2? Just e to the log 2, right? Okay, so let's talk about this then. How do we simplify that? And this goes back inevitably to our review. We got to kind of add on to our review of pre-calc review of logs and exponentials. There's 2 ways we can think about this. So everybody close everything up for now because this is not negotiable. You got to watch this one. This is going to be very helpful. So we could do this a couple ways, right? We could think of this as we could write an equivalent statement, right? We know that we can always write an exponential statement as a logarithmic statement. Yes, sir.
How did it go from 1/2 to
2 times 1/2.
Oh.
Right? Okay. So we know that we had a property of logs we discussed the other day, and you guys all told me this. If I have the statement, we're starting with an exponential, so if I have something like y equals e to the x, what's the equivalent logarithmic statement? right? We said a log is an exponent, so how can I rewrite that using a log instead of an exponent? Okay, so the base of the exponential is e, so the base of the log is e, right? The base e log of what? Of y equals x, right? Because a log is an exponent. Whatever the log is equal to has to go in the exponent of the exponential statement, right? So how can we apply that here? Well, what's this going to mean then? So we know that we have the base e log of y, right? You can't. That's the, now, we'll talk about that other approach also. Right, so the base e log of whatever's on the other side has to equal the exponent, right? A log is an exponent. So what's true then? If the log of y equals the log of 2, then what has to be true?
Y equals 2.
Y equals 2, right? Okay. So that's the way I believe you guys did this last year. You always, and correct me if I'm wrong, but did you always write equivalent statements to transition between exponential statements and logarithmic statements? Okay.
We didn't do that. We didn't do a little bit from last.
Not a lot. Okay, well, then I think we need to fill in a little gap there. I think because that's really, not only is it important in calculus, it's just a really important part of math. So I'm just gonna, I think we need to build in some time for that.
Didn't you already give us, you gave us one on the properties of logs already?
Yeah, we talked about properties of logs.
So.
But there's another part of this, there's a lot more to it than that, though. Because I'd like you to understand, I want you to know what they are, and it leads into some really cool calculus. But I want you to kind of know, what they are, what they model. You want to be familiar with the models, right? We did a lot the other day, but I still think maybe it's worth just rehearsing that. I know, who was not, I know Kirk, you weren't here for it. Who else was not here for the log review? Anybody else was? Okay. We said a couple things, right? We said that we have some properties of logs. Logs bring us down one step on the complexity hierarchy. If you think order of operations stuff, right, they move you down one rung. If we think, remember this stuff? We can ignore parentheses. Logs move you down. So if I have the log of a product, we go from the product to what? Yeah, it takes you straight down to addition, right? So we're going to write that as log A plus log B. Okay, if you have the log of a quotient, that takes you straight down one layer from derivative, or not derivative, from divide to subtract. Log A minus log B. And then finally, that's kind of an awkward color. Finally, if we've got an exponent, the log of A to the m, it takes us down from exponent to product, right? So it becomes m log A, right? Everybody see that? Here's just another, I just can't resist. How could we combine this guy and that guy to come up with the quotient rule for logs? Because I think if you see these connections, it really helps. Like if I started with, for example,
You've got A times B to the negative 1.
yeah, exactly, right? So we could start here and we could say the log of A over B equals the log of A times B to the minus 1, right? And by our properties of logs, that's the log of A plus the log of B to the minus 1, right? But then I've got my exponent rule, so I could bring the exponent out front and make that the log of A minus the log of B. Right? So I combine these two to give us the middle one. Right? Okay, so we also talked about the inverse nature of logs. I can't remember where we left off on that.
How about you just keep on building questions, then you, it's all about logs tomorrow.
Okay. We can do that. But on this problem then, so are you guys okay with the idea that, this is just equal to 2? Everybody get that? That y would have to just equal 2?
Yeah.
Okay?
Why? Oh, okay.
Right? And then we can even look at that as an algebra step. When we finish our review of logs, what I want you to see is that what I've done here is I have applied inverse functions of each other, and so they undo each other. Exponentials and logs undo each other, and so the e and the natural log would cancel and just leave me with a 2. But we'll get there soon. Okay? So we know y equals 2. So there's our other. There's the y coordinate of the point of tangency. Now we just need a slope, right? Well, the slope is going to be y prime where? At x, right? Good, so it's going to be y prime at x equals 1/2 natural log 2. So we would have to just evaluate the derivative at that place. So what is the derivative? If y equals e to the 2x, what's y prime? Times 2, because we have a chain rule issue, right? We have e to the hand, but hand is not x, it's 2x. So y prime equals e to the hand times the derivative of hand. So then at x equals 1/2 log 2, y prime equals 2 times e to the 2 times 1/2 log 2 is just log 2. Agreed?
Wait, did you, what?
I won't skip that step.
Why am I so confused right now? Okay.
So we found y prime, right?
Yeah.
So we're just going to evaluate y prime at x equals 1/2 log 2. 1/2 log 2 is just a number, right? There are no variables in that. Plug that in the calculator, I just get a decimal number back, right? So if I plug this into my derivative function, which is really all I'm doing, I get 2 times e to the 2 times 1/2 log 2. So those cancel. I just get 2 times e to the log 2, but we already found that e to the log 2 is just 2. Right? So there's the slope of the tangent line. Here's our point of tangency. Now we just write the equation of the line. Yeah, I know it's a little strange, but that's really all it is the equation of a line. So let me grab just that information and go to the next page. So all we're doing then is just combining those two pieces of information into a line. Right, now all we have to use is we can use point slope form. So y minus 2 equals m times x minus 1/2 log 2. Y minus y1 equals m times quantity x minus x1. Right? Now I just have to simplify. distribute 4. So I'm gonna get 2, log 2, just add 2 to both sides and you're done. I mean, really, that's fine. Right, that's the equation of the line, but if you wanna put it in slope-intercept form, y equals mx plus b.
Can we change math Excel so we can't put it in point intercept form? Slope form?
No, I can't really, I could, but I don't, so you guys will just like have to do that. But it's, like in college, that's that's gonna be fine. Because if I were to graph that, I'm gonna get the same line there that I get there. Okay? That help? How much time we got? Okay, keep plugging away. We'll continue maybe reviewing some log stuff tomorrow. And then we'll